Hello everyone, in this video we'll be starting with a new series for deep learning using Keras. In today's video we'll be implementing a simple neural network using Keras, and the dataset that we'll be using is the iris dataset. It's a simple dataset. You can go online and search and you can get some information. Basically, as you can see over here, you'll have sepal length, sepal width, petal length, petal width. Okay, but let's start. First, we are going to import the basic libraries. So pandas as pd, numpy is np, and matplotlib for plotting the various graphs. For getting the dataset, what you can do is either you download the dataset and upload the dataset to your local drive over here, or what you can do is directly give the URL over here. I'll be giving this URL in the description, so don't worry. You just have to copy paste and hit click. You can either click over here or you can hit shift and enter just like me and get the dataset. So df.head is going to give you the basic top five rows of the dataset. So you have the four attributes, as I said: sepal length, sepal width, petal length, and petal width. So what these attributes mean? So what I will do here is, as you can see over here, this is the uh, these are the three classes that we have in the dataset. There is iris versicolor, setosa, and virginica. So what I mean by sepal is this thing. Okay, so it has a kind of a stem, and then there is there's a flower on top over here, and this is called sepal. And petal, you can see, it doesn't have that stem over here. It directly has the flower. So this is the petal, and this is the sepal. So sepal length is this over here, and sepal width obviously is this. And same thing for the petal length is this, and petal width is this. Okay, so this is for versicolor, same thing for setosa and virginica. Okay, so we have seen this data set over here. What I'm going to do is, you can skip it, but I generally like changing the names of the column. So instead of having sepal length, we'll have sepal underscore length. Same thing for sepal width, petal length, and petal width. More importantly, the name column over here, which we are going to predict, is changed to the variety column that you can see over here. So let me go and run this particular cell. After that, we will see whether the changes that we needed has been shown and reflected. Yes, we can see the name has changed to variety. Now what I'm going to do is, I'm going to take the basic let's say the features. So our features are sepal length, sepal width, petal length, and petal width. Variety is what we have to predict. So the way I'm going to separate the features is, I'm going to take the df, that is this data frame, and then I'm going to drop this particular column. So whatever is left over here, these four columns are going to be our features, as you can see, and then I'm going to print. Okay, so as you can see over here, our sepal length, sepal width, petal length, petal width is there. However, we have successfully dropped the variety column. Okay, and what is going to be our target? It's obviously going to be df.variety. So when I did df.drop, I did not write in place equal to, I did not write in place equal to true. So let's say if I wrote in place equal to true, then the data frame would have deleted the variety column completely, which I don't want, because I just want the features to be in X. And the way I have taken the, as you can see over here, if I just copy it from this df.variety and I'm sorry, and you paste it over here and then shift enter, what you will see is that the target column is shown. But the problem with this target column is that these are not numbers, these are text. And again, as I said, the problem with deep learning neural networks is that they don't understand text. They have to be converted into numbers, and thankfully pandas gives you that ability to do that. So what you do is, you pass this particular column df.variety and pass it through a function pd.getDummies, which I'm going to explain what it does. Basically, it converts it into a one hot encoding. So now let's see what is one hot encoding. So we have seen this sepal length and sepal width. Now we also know in the data set that there are only three classes. As you can see over here, versicolor, setosa, and virginica. So setosa is being given a representation of 100, versicolor is given the representation of 010, and virginica is given the representation of 001. So anytime we have setosa, we will not be saying setosa, because computers don't understand text. We will be saying 100, and same for versicolor and virginica. Okay, so this is something that we need to make sure. that we have, and here I'm going to hit shift and enter, and let's see why. Okay, so you can see Satosa, the first one, let me go and show it to you. The first one, the first row is Satosa. Okay, now if you remember from there, I said Satosa is 0, Satosa is 100, and you can see over here in the Y data frame, Satosa is 1, and the rest everything is 00. Last over here you can see it's popping over here Virginica. Okay, so Virginica is 01001, Virginica is 001, and you can come over here and see it is also 001. So I hope you understood how this works. So now we will be looking we will be looking into train test split and see actually how it works. So this was our data set. Remember, we took X, we dropped this Y, and we used the PD dot, what is the function? PD dot get dummies, which basically converted into one hot encoding. And this was our features. Okay. So we are going to do train test split. Now, why do we need train test split? Obviously, whenever you are using a machine learning or a deep learning model, you want the data set to be divided into ideally 3 parts, but generally we, for validation, but you can also get away by doing it into 2 parts, that is training and testing. You can take any ratio, generally 0.3 for testing or 0.2 for testing, and 1 minus whatever is the testing split, it goes to the training. So 0.8 or 0.7, whatever it is. So this was our, and I'll explain what that means. So this is our features. Now what you do is 80% or 70% of these rows, of all the rows, so there will be 150 rows because there are 150 examples in this iris data set. So obviously you'll be taking 80% of that or 70% of that, and then using that we will create the training data set. Similarly, let's say if the first row is taken in the training data set, in the training split, then the Y train will also have the first row. Okay, so as you can see over here, the training data is shown in red and the testing data is shown in blue. So as you can see, there are more red than blue because obviously we are taking only 30% as testing and 70% as training. So the first row here you can see is bracketed in red, which means this is a part of the training data set. So you can see the sepal length is 5.1, sepal width is 3.5, petal length is 1.4, and the petal width is 0.2. And correspondingly, you also have an entry into the Y column, which is the target, and it is being predicted as Satosa 100. Okay, same thing, but this time we have a blue row, and this is going to be in the testing data, as you can see over here. So 4.9, 3.0, 1.4, and 0.2, and correspondingly you also have 100. Same thing for all the other rows. You can see this one is red, this one is red, this one is red, this one is red. All these will be going into our training data set, and the blue ones are going to be in our testing data set. So once you do that, what will happen is you'll have 4 different portions. So X train, X means your features, and train means it is going to it is going to be used for training. So you can see these columns over here. This was the training data set. This is 70% of the data set. You can see there are many rows over here. Yeah, at least 5 is there, and these dots means there are going to be many rows over here, and correspondingly whatever the predicted class was there is shown over here. Then you also have X test. This is going to be used for testing. Okay, so you can see there are a few lesser number of rows compared to training because we are only taking 30% of the data set. And similarly you also have Y test, that is correspondingly the classes that needs to be predicted. Okay, so you can use the train test split function from sklearn.model prediction, and the way you use it is you say x train comma y x train comma x test comma y test. So this is how we do it. And train test split, you take the features, which is x, you take the target, which is y, and then you specify the test size, which I have specified as 0.3, which means 30% of the data, of all the data, is going to be used for testing, which means 1 minus 0.3, that's 0.7, is going to be used for your training. So now we have divided. Let's see what we have in the testing, or rather the training data set. So let me go on the top. Yes, so you can see there are certain values over here, though the indices has been messed up, and this was something that is required. I showed there. As you can see over here, there is no specific ordering between the red and the blue, which means that this this is totally random. This could have been blue and this could have been red and all those things. Okay, so you have the X train, you also have the Y train, which is the corresponding values for. So the first one you can see is the versicolor, which is the 65th. 38th is Setosa, as you can see over here, 100. Now let me go below. Obviously here what we have is we are going to start building our model. So from Keras you have to import sequential, and then from Keras you have to also import keras.layers, import dense. So dense is used for creating linear layers, as we say in PyTorch, or just simple neural network layers. Okay, so I'll hit shift and enter, and this is going to be our model creation over here. Now I'm going to explain in detail in the PPT how this works. So model is equals to sequential. This is just basically the statement stating that we are going to have a sequential neural network, nothing more than that. And then you add two dense layers. Okay, you can see over here dense units 6, and I'm going to explain what unit 6 means, and activation sigmoid is basically the activation function. I'll be creating another video discussing the different activation functions and how they are used, where they are used, when they are used, and all those things. You are having another dense network, which we'll see in the PPT in just a second. You're going to have 3 layers, and this will be the number of classes that we are predicting, that is Setosa, Virginica, and Versicolor. And the activation for more than multi-class classification is generally softmax. I'll be having another video in explaining those activation functions. So let's go to the PPT. So this is the neural network. Now you can see there are 4 neurons over here in the start. So this is one layer. When you see this network, this is nothing but a matrix. Okay, if I can let me just use a ballpoint pen. So this particular layer is nothing but a matrix matrix of what size? So as you can see, there are 4 inputs. So this is 4 cross, so I'm using the mouse to do it, and that's why it will be slow. And how many layers how many neurons are there in the hidden layer or this middle layer? There are, as you can say, 6. So this matrix will be of size 4 cross 6, which means there will be 4 cross 6, that is 24 different weights. And let's say they are also biases, so let's say 6 biases, but we have not considered biases over here. So this is basically a matrix. Any linear layer in any neural network framework or machine learning framework, deep learning framework, doesn't matter, PyTorch, TensorFlow, Keras, wherever, it is simply a matrix. A neural network layer is nothing more than a matrix. So the matrix input is all the features. So there were 4 features, if you remember: sepal length, sepal width, petal length, and petal width. So there will be 4. This is the 4 over here. And 6 is basically what we can change. You can change it to 7, you can change it to 10, you can change it to 2. It doesn't matter, it is totally in your hands. It's a hyperparameter that you can change and see how your model works. Okay, and again, as I said, this is another linear layer over here in between, which means this is another matrix. Now if you can guess what is the input and output size of this matrix, or basically the dimensions, this is 6 neurons here. So this is going to have 6 cross, any guesses? Obviously there are 3 neurons here, so this is going to be a 6 cross 3 matrix. Okay, nothing fancy over here. So the diagram states that all your features will be fed into the first input layer. So this is called the input layer. Okay, this is called the hidden layer, and this one is called the output layer. So you're going to give all your features over here. So this features is going to be of the size, I'll tell you, this is going to be a vector of size 1 cross 4. Okay, so obviously you are going to multiply a matrix of 1 cross 4 into 4 cross 6. As you know, this has to be same, and your output will be this, which is 1 cross 6, which is going to be over here, and this output is going to serve as an input of this to this matrix. So as you know, 1 cross 6 from here, so you'll have 1 cross 6 over here. And then again, the same idea, these two things have to be similar, and the output will be this 2, that is 1 cross 3. And you can see over here you have 1 cross 3, or 3 neurons. So this is how it works. Okay, so you'll be giving 4 features. one matrix multiplication will happen over here, you will be getting an output. That output will be given to another matrix multiplication will happen over here, and then finally you will have an output which is of size 3. And what are these neurons representing? The first neuron is going to represent the first class. So whatever values over here we can see we'll see in the next slide, it will be considered as the probability of setosa. Similarly, this neuron will tell you the probability of versicolor, and this one is going to tell you the probability of virginica. Obviously, these are probabilities, which means they will all be values between 0 and 1. And later you will find out that these values also need to come to 0, because this is going to, we are going to add this up, and the addition needs to equate to 1. Okay, we'll be looking into this later. Okay, so let's go to the next slide. So how things will work? So if you remember the first training sample, which is this one, so sepal length is 5.1, sepal width is 3.5, petal length is 1.4, and petal width is 0.2. Remember these values: 5.1, 3.5, 4.1, and 0.2. Aren't these the same? 5.1, 3.5, 1.4, and 0.2. So this is a vector of dimension. If you remember, this is going to be 1 cross 4, which is going to be fed into which is going to be multiplied by a matrix of 4 cross 6. Correspondingly, you'll be getting 1 cross 6, which will again be multiplied into 6 cross 3, 6 cross 3, and then finally you'll be getting these three. As I said, these three values will be over here. They will be normalized. You know, there is a softmax activation function which I have not shown over here, but there are, again we'll have to make another video specifying that. But there is sigmoid activation function. You can use ReLU also over here. I would rather say you use ReLU, and here you will use a softmax function. And these, all these values, if you sum them up, it will turn into 1. But remember, in the data set we found that this particular sample in the training data set corresponding to setosa, but over here you can see the maximum value is coming from what is this, a versicolor, which means this model, which has not been trained or not has or hasn't been adequately trained, is considering that this particular sample which we have given actually belongs to the versicolor class. But that is wrong. We know that this is from the training data, and hence we have the label, which means we know that this belongs to the setosa class. So what we are going to do, we will try to make sure the model behaves in such a way, we will try to train the model in such a way that our probability of whenever this particular sample is given, the value of this turns higher, that is, it goes up, because we know this is setosa, and all these values go down. And how do we know it? Obviously from the training data set. So as I said, you wanted a 1 over here because you were sure, because this is a training sample, that this belongs to setosa, this particular input, and this is not 0.49 and this is not 0.27, this is 0 and 0. So we will have to calculate something called as error. Now what are these errors? We'll basically try to find cross entropy. There is already a video on my channel explaining what these are, but I'll not be getting into that right now. I'll be going into that in another video. But basically what it says is the probability of the predicted class has to be high and rest others has to go down. Okay, now there is math involved. Obviously it's kind of an involved derivation which I don't want to get into right now. So let's go back to training. Okay, so I hope I was able to explain this model, why this 6 and why this 3. Now let's hit shift and enter. After that, so all these things: optimizer, loss is equals to categorical cross entropy, metrics equal to accuracy. This is obviously things that will come in the next video, but you will have to use this. So you can basically hit shift and enter, and finally we will hit over here. So model.fit basically trains the model. We are giving the training data set, training features, then training values, the the output values. We will be training it for 25 epochs. Epochs is basically how many times the model has been run on the data set, and batch size is 5, which means that every time we are giving 5 examples to the model. Okay, so let's hit shift and enter and see how long it takes. Okay, so the model has trained. We started with a 0.2857 accuracy and a loss of 1.307. 3017. Then after 25 epochs, you have seen that the loss has reduced to 0.8330, and we have gotten a 71.43 accuracy. Obviously, if you train it for a little bit more, you'll get more accuracy. Okay. Or depends on the data set also. There are a lot of things that work. Now let's see how our model is performing on the test data set. So we have seen our accuracy is 71 in the training data set. Now let's see on the test data set. So we have secured a 55%, which is not that good, but okay, fine. It's better than, a little bit better than a toss of a coin, which is a little bit acceptable. Accuracy is 55%. I think if we train for a little bit more number of epochs, this should work. So let's just consider this only and then fit it again. 70%, 71%, 76%. So slight increase over 71 point something percent. And then again test it. Same. Okay, it doesn't matter, sometimes it's a very small data set. It's not even it does, I don't think even that deep neural network model can train on let's say a simple iris data set, because generally deep learning models require a lot and GBs of data, not some KBs of data. But whatever, it explains, it serves the purpose of explaining how neural networks work. Now model dot predict. So we are trying to predict on an individual um, let's say an input. Let's say our sepal length is 5.1, sepal width is 3.5, petal length is 1.4, and petal width is 0.2. So this is completely a random vector that I have generated from my own mind, and let's see what it is classified as. So you can see it is 81.2% almost certain, and this adds to 1. Okay, that is what I was saying, that it has to, these are probabilities which have to add to 1. So it is, this model is almost 82% sure that this particular sample that I have given belongs to the Setosa class, that is 100 class. Okay, so this is how you use a simple neural network to work on an iris dataset. Obviously this is a very simplified kind of an example. There can be a lot of things that we can do. In fact, I believe that iris dataset is something that we don't even train on a neural network, because the dataset is just too small. But obviously there are other things that we can consider. I hope you enjoyed the video, and please like and subscribe to my channel. Thank you very much.